Welcome to Study Loop.
We're given an ideal gas that is going through compression at a constant temperature, but we know the final pressure after compression will be the pressure given here. It is given in the problem, and we're asked to find the initial pressure if we know the final pressure. So in order to do that, to derive the equation for P2, we need to start from the general expression of the work done. So the work done is an integral from first volume to the second point of the pressure function as a function of volume, differential of volume. We know that the pressure times the volume from the ideal gas law is going to be N times R times T. So we can substitute that in order to obtain nRT over V. This gives us the integral form, which is the constants will go outside of the integral and RT, and inside of the integral we will have from V1 to V2 1 over V dV, or the differential of the volume. This is a table integral, so the solution for all integrals of this type, 1 over argument times differential of the argument, are natural logarithm of the argument. This is for the unbounded integration, and for here we have a bounded integral, so for the bounded integral it is going to be like this. V equals nRT, and here we have natural logarithm of V2 minus ln of V1. From the rules of natural logarithm, we can rewrite this as natural logarithm of V2 over V1. Also, we have to remember that for ideal gases, so we have the law of inverse proportionality between the volume V2 over V1 and the pressure. So the pressure will be P1 over P2 because it is inversely proportional to each other. This can be used to express the work done as nRT natural logarithm, but this time it will be P1 over P2. Now, from here we can start to derive the equation for P1. So first thing we need to do is to raise both sides as powers of E, which gives us the work as a power of E equals E to the nRT, and since E and ln are inverse function, we will have just pressure 1 over pressure 2, which is very important since now we can actually derive the equation. We can move the terms from the right hand side to the left hand side and from the left hand side to the right hand side to obtain this form. P1 over P2 will be equal to E over on the work done and nRT here. So it will be wise to evaluate this exponent on its own. So just work over nRT will be equal to, this is going to be a numerical calculation, so this is going to be minus 468, and down we'll have 0.305 times 8.314. This is for the gas constant, and for the temperature it is going to be times 295 0.15 kelvins. And this is going to be equal minus 0.625. This is a dimensionless number. And from here we can finally say that P1 is going to be equal to P2 times E on minus 0.625. Now we can substitute for the P2, so this will be 1.76 atmospheres. This is the physical quantity for it, times e to minus 0.625. And when we put these values into a calculator, we finally obtain the answer, which is that P1 equals 0.942 atmospheres. And this will be it for the part A of the problem. Now for the part B of the problem, we need to sketch. We need to sketch the graph, pressure versus volume graph. So this will be part B. Let's say that this is a pressure axis, P, and that this is volume axis. So the first point will be the point before compression. So this is going to be volume 1. And the corresponding pressure will be pressure 1, or the initial pressure. So this is having coordinates P1, V1. And isothermal process means that the temperature will not change, only force is being exerted, it's doing work, and it's increasing the pressure. So here we will have a small curve like this, and this is the point 2. So this is point 1, this is point 2, phase 2. And it will have P2 as its corresponding pressure, and much smaller V2 as its smaller volume. So for this point it will be P2 and V2. And this kind of graph is expected, so this is the direction. It is going from 1 to 2 and under constant temperature. By creating this sketch, we have finished the problem. We did all the parts, and I hope you found this helpful, and I hope to see you in the next class. Bye!